Hello everyone. So in today's lecture, this lecture is lecture 7.1 of power system stability. In this lecture, we are going to discuss a numerical example to explain the importance of maximum steady state power capability and how to find the maximum steady state power capability of a system consisting of a generator connected to an infinite bus. Let's start. Let me take the drawing tool. Okay. You are asked to find the maximum steady state power capability. Maximum steady state power capability of a system consisting of a generator. That means this is the generator. Let me represent the generator like this. This is the generator with equivalent reactance of 0.4 per unit. So in series, I am representing the generator equivalent reactance as 0.4 per unit. Then it is connected to the infinite bus through a series reactance. So it is connected to the infinite bus through a series reactance. So this is the series reactance, and the series reactance is 1 per unit. 1 per unit. Now this is the infinite bus. This is the infinite bus. Now it is also given that the terminal voltage of the generator is 1.1 per unit. So this is 1.1. This is 1.1. Let the angle be theta. I am assuming the angle as theta. And here we have the generated EMF EG with angle del. And it is also given that the infinite bus voltage is 1 per unit. So I am taking this as a reference. I am taking infinite bus voltage as a reference. So this is 1 angle 0 degree. And del is, this EG is obviously leading the infinite bus voltage, so that the power flow is in this direction. This is the direction of power flow. Okay. Now you are asked to find the maximum steady state power capability. What is the condition for maximum power transfer? The condition for maximum power transfer is that del equals 90 degree. Del equals 90 degree. Now let's write the equation for this circuit, this equivalent circuit of the system. This generated EMF EG angle del equals the terminal voltage VT. This is the terminal voltage of the generator VT plus J into XD into I, where XD is 0.4 per unit. This is 0.4 per unit. Okay. Into I. I is this current. Let I be this current. Okay. Now, let this be equation 1. Sorry. Let this be equation 1. Now, what is I from this equation 1? I equals, how will you find I? I can be written in terms of infinite bus voltage as terminal voltage minus infinite bus voltage. This is, let it be infinite bus voltage. Okay. Terminal voltage minus infinite bus voltage divided by Jx. This X is series reactance 1 per unit. Okay. This X is series reactance. This is 1 per unit. This one. Okay. This one. Okay. Now, this is I. So if you substitute this I in equation 1, you will get EG in terms of VT and V infinity, right? So let it be I equals, your VT is 1.1 angle theta minus infinite bus voltage is 1 angle 0 degree divided by Jx is 1 per unit. So J1, right? J1. Now, let this be equation 2. Let this be equation 2. Okay. Now, from 1 and 2, from 1 and 2, we can substitute I in equation 1. That is, we can substitute equation 2 in equation 1. So this EG angle del will become 1.1 angle theta plus J 0.4, right? XD is 0.4, J 0.4 into this one, 1.1 angle theta minus 1 angle 0 divided by J1, right? Let this be equation 3. Let this be equation 3. Okay. Now, let's move on to the condition for maximum steady state power capability limit. The maximum steady state power capability limit is reached when del equals 90 degree. So in equation 3, if del is 90 degree, what happens to the RHS? If we convert the RHS into rectangular form, here some polar forms are there, right? Completely, if we are converting this RHS to rectangular form, then there will be only imaginary part and the real part will go to 0. So if real part of this equation, real part of equation 3 is 0, if that condition is applied and theta is found out accordingly, we could find the maximum steady state power capability limit. Now let's find, we'll convert this to rectangular form by this 1.1 angle theta can be written as 1.1 into cos theta plus j sin theta, and this also same 1.1. So basically here theta is the only unknown, right? And you get that mod EG equals, that means let me mod EG angle del equals, after simplifying we get this as 1.4 cos theta minus 0.4, this as real part, okay, this is the real part, plus j into 1.54 sin theta, So let this be equation 4. Okay, let this be equation 4. Now I am equating the real part to 0. That means this 1.54 cos theta minus 0.4 equals 0. From there I get theta. Theta is evaluated as theta equals 74.9 degree. And we know that mod EG equals 1.54 sin theta. Because real part is 0, right? Real part is 0. So mod EG equals 1.54 sin theta. Now, if mod EG, then you are getting mod EG as when you substitute this theta equals 74.9 degree here in this equation, then here in this equation, then you are getting this mod EG as 1.486 per unit. You can check it, recheck it. Okay, I'm just explaining the concept. Now, VT. What is the terminal voltage? Terminal voltage is 1.1 angle theta, right? So theta is now evaluated. So 1.1 angle 74.9 degree. Now, what is the maximum power capability, steady state power capability limit, Pmax? You know that Pmax equals mod EG into mod V divided by, here total reactance is XD is the generator reactance plus this is the series reactance which is connected to the infinite bus, through which the generator is connected to the infinite bus. So XD plus X is the total reactance, which is equal to 1.486. This is 1.486 into 1. Infinite bus voltage is taken as 1 divided by 0.4 plus 1, which is equal to 1.061 per unit. 1.061 per unit. So this is how we find the maximum steady state power capability limit for a local generator connected to an infinite bus through a series reactance. The same concept can be applied to a sending two different power system buses where a sending end is there and a receiving end is there, and the power flows from the sending end to the receiving end. Instead of EG and V, it will become V sending and V receiving there, and the reactance in between V sending and V receiving, the total reactance should be considered while finding it. So that's all with this numerical. We will start with the introduction of equal area criteria in the lecture 7.2. Thank you.